Let's take a look now at correcting vision with converging and diverging lenses for both nearsightedness and farsightedness. We'll start with myopia or myopia. So for a person who is nearsighted, nearsightedness, there's some confusion around the terms. If you're nearsighted, that means you can see things that are near well, and you have a tough time seeing things that are far away. If you're nearsighted, you have a tough time seeing things that are far away. So when you solve problems involving the correction of myopia, you're going to use the far point, FP. We'll see what that means in a moment. And you will also use a diverging lens. I would just try to memorize these connections. Problems involving the correction of nearsightedness involve the person's far point, which I'll define in a moment, and the use of a diverging lens to put the image where it needs to be. For hyperopia, people who are hyperopic, otherwise known as farsightedness, and I sometimes wonder why so many of us have these vision defects. How did we ever survive in the wild with these severe vision defects? I guess if you were able to see far, you'd still be a good hunter. And if you were still able to see near, you could prepare food, make tools. You'd still have some usefulness in your tribe. So for people who are hyperopic, they can see far away from them. They're good at seeing things that are far away. They have a tough time focusing on things that are near. So for those people, you would use their near point, which I'll define in a moment, and a converging lens would be used to correct the defect. That sounds so cruel, a defect in your vision. And in all cases, regardless of whether it's a nearsighted person or a farsighted person, all the images that we're dealing with are virtual images, which means your image distance is going to be a negative number. Keep that in mind as you're doing these problems. So let's take a look now at some images from your book. Your book talks about the ciliary muscles which surround the lens of your eye. Let me maximize this. As your book points out, the majority of the focusing actually happens at the front of your eyeball, the cornea. The lens only makes small corrections, and you can understand that if you keep in mind that the index of refraction of the fluids on either side of the lens, those indices of refraction aren't very different from the lens's index of refraction. So when you go to apply Snell's law, you find that there's not a whole lot of bending of the light that happens within the eye. Most of it happens at the surface. Okay, so this is a, quote, normal eye. It's something like 1 inch from the front of the eye to the retina, thereabouts 1 inch. FP stands for far point. So a person with normal vision, I suppose you could call that 20/20 vision, when their ciliary muscles, those are the muscles right here, when they are relaxed, in other words, the lens is in its relaxed state, an object at infinity will produce an image sharply focused on the retina. So for a person with normal vision, when their eye is most relaxed, they can look at an object very far away, a mountain, the moon, and the image of that object will be perfectly or near perfectly focused on their retina. Now, if they want to look at something closer, see how the lens here has gotten a little thicker in the middle than it was up here? If the lens in the bottom picture had the same shape as the lens at the top, then this image would actually focus behind the retina. In other words, it would be blurry at the retina. And so to accommodate the new location of the object, in order to accommodate this object position, the ciliary muscles have to contract and cause this lens to bulge a little bit, which would shorten its focal length. And you could use the thin lens equation to make sure that when the object point, or when the object distance is 25 centimeters, the image distance comes out to be 1 inch approximately, so that it focuses on the retina. NP is for near point. So 25 centimeters is taken to be a typical value of the near point for a young adult with normal vision. As your book points out, when people get older, their near point tends to increase. I believe that's called presbyopia. It's a normal consequence of aging, and I guess it has something to do with the fact that this lens becomes less flexible. Children have an even shorter near point. They can put things even closer to their face and still be able to focus on it. You might try it yourself. You know, grab a sheet of paper with some notes on it. See how close you can hold it in front of your face and still be able to read it without your glasses or your contact lenses. Okay, so this is how a normal eye is supposed to work. But let's take a look at, first, this is farsightedness. So a person who is farsighted, that means a person who's able to see things far away, but they have a tough time focusing on nearby objects. That person, very often, the cause of their farsightedness is short eyeballs. Their eyeballs are a little shorter than they should be. The dashed line here is showing you where the back of the eye should be. This eyeball is a little bit shorter. And as a result, if you were to put an object 25 centimeters from their face, now a person with normal vision would have no trouble focusing this image on their retina. And I probably should have mentioned in the previous slide that the significance of the near point is that's the closest you can get. Any closer, like if this was a flower you were looking at, if you put it any closer to your eyeball, your lens would simply not be able to accommodate enough. You couldn't make the lens bulge enough so that its focal length was short enough to put the image on the retina. So scoot this object any closer, and these rays would focus back here somewhere. In other words, they would be blurry on your retina. This is the closest you can get to your face. Okay, so back to this far-sighted person. They should be, ideally they would be able to see this object, but you can see that because the eyeball is too short, the rays are converging to a point behind the fovea, or that's the center of the retina. Okay, so this person's actual near point, NP for near point, the near point of the far-sighted person is greater than 25 centimeters. This is the closest you can place an object. This is the closest that you can place an object and still have that person be able to focus it on their retina. So the idea is a far-sighted person, somebody who can see far away easily, they would still like to be able to read a book up close to their face, or see the tomatoes clearly that they're dicing on the cutting board. They still want to be able to see things up close. If they're standing face to face with somebody, they would want to be able to focus on that person's face, even if that person is closer than their near point. And their near point could be out there at 100 centimeters, 150 centimeters, over a meter. There's plenty of situations in daily life where you would like to focus on something closer to your face than just 1 meter. So the idea is to insert a lens between your eyeball and the object, and you'll note that this is a converging lens. Remember what I wrote down a moment ago? For a person with farsightedness, you would use a converging lens. And this doesn't look like the typical converging lens that we often draw, but notice that it is thicker in the middle than it is at the edges. Hence, it's a converging lens. The object is still placed, let's see, let me take that back. Now, you actually can place the object 25 centimeters from the face. So try to get this straight. This 25 centimeters is not the far-sighted person's near point. This is where the near point should be for somebody with normal vision. So now you really can put the book page or the recipe that you're reading or the person's face. You can put it 25 centimeters from the far-sighted person's eyeball, and what the lens will do is take that object and produce a virtual image out at the far-sighted person's actual near point. The whole idea is to take whatever it is you're looking at and produce an image of it at the near point of the far-sighted person, because this person's eyeball is able to focus an image of an object that's at the near point. So once again, to correct farsightedness, take the object that you want to look at, put it 25 centimeters from the person's face, which is a normal person's near point, and have a converging lens produce a virtual image which is out at the actual near point of the far-sighted person. So in this case, near point is not 25 centimeters. It's this much greater distance. Could be 150 centimeters even. Depends on the individual. And you should note that this is a virtual image. See the dashed lines here indicating that the rays do not actually converge there. They appear to be diverging from there. So this is a virtual image. And don't forget, if you're using a converging lens, the only way to get a virtual image is to put the object inside the focal length. Since this object is 25 centimeters from the lens, don't worry about this extra distance between the lens and the eyeball. Since this object is 25 centimeters from the lens, and we know that it's inside the focal point, that means the focal length of this lens must be greater than 25 centimeters. Let's take a look at correcting, or an example of correcting farsightedness, otherwise known as hyperopia. Remember that when you're correcting farsightedness, you need to talk about a person's near point. This person can only focus on objects that are far away. They have trouble focusing on objects that are close to their face. So the relevant number is what's the closest they can get before they can't focus anymore. That would be the near point. A normal eye would have a near point of something like 25 centimeters. Because this person is farsighted, their near point is way out at 110. They cannot focus on anything closer than 110 centimeters without a corrective lens. So here's a very horribly drawn eyeball. If you placed an object like a flower, 25 centimeters from this person's eyeball, the rays would not bend enough to focus at the retina. They wouldn't converge until they're at some point behind the eyeball. And again, that's partially because, or maybe it's mostly because, their eyeball is too short, a little shorter than it should be. So the idea is, if this object was way the heck out at 110 centimeters, they would be able to focus on it. So let's take the actual object, let's put the flower 25 centimeters from their eyeball, but now insert a converging lens that will produce a virtual image of this object way out at 110 centimeters. So my drawing is not as good as the diagrams in the book, but what I did was bend this ray. This ray I didn't bend because it's passing through the center, or the optical axis on the curvature of the cornea, so it should be undeviated. But I'm imagining that this ray gets bent by the lens so that the two rays really do converge on the retina and form a focused image. But that means that this ray appears to be coming from back here, and now I can go ahead and extend this line backwards. This object that you're looking at would seem like it was way back here. And if something is way out at 110 centimeters, this person really could focus it on their eyeball. And maybe you're thinking, wait a minute, wouldn't that make this object seem enormous to the person wearing the glasses? Yeah, my diagram's not perfect. This actually would have a larger or smaller angular size than the image. So you don't take everything about this diagram literally. If you want to get a better idea here, let's go back to the book's image. Yeah. Here is the actual object. Let's say it's the penny that you're looking at, and the rays are bent so that they appear to be coming from back here. Here's the virtual image, which is out at, for this problem, this would be out at 110 centimeters, the far-sighted person's near point. Okay, now let's plug in some numbers here. All we're using is the thin lens equation, because we have a single thin lens. 1 over S plus 1 over S prime equals 1 over F. If you've read the chapter, and I sure hope you have, you've learned that optometrists, people who make lenses, rather than talk about the focal length of a lens, they prefer to talk about the power. And it's very simple. The power is the reciprocal of focal length. So what we're talking about here is the power. We're already looking at the power. Units of diopters, well, the SI units would be inverse meters. Focal lengths in SI units would be in meters. Take the reciprocal, we're talking about inverse meters. So a diopter is an inverse meter. It kind of makes sense that they call it power because a lens that has more converging power would be a lens with a shorter focal length. The shorter the focal length is, the more the rays are bent by the converging lens, and the smaller f is, the larger the reciprocal is. So short focal length means high power. Okay, we're supposed to figure out what is the lens power in diopters. In other words, what should be the reciprocal of the focal length of this converging lens. This is what we're solving for. Okay, well, where was the object actually placed? The point is that you would like to be able to put the recipe book, or hold it in your hands 25 centimeters from your face. So the object distance is 25. The image distance, we want the image to show up at the far-sighted person's near point so that their eyeball can actually focus those rays on the back. Here's one way to think about it. After the lens has done its work of converging the rays, pretend it's not even there. Get rid of the lens in your mind and just imagine something out here whose rays actually could be focused by the front surface of the eyeball, the cornea. Okay, so the image distance needs to be 110. That's the near point. Don't forget that the image distance is negative. It's a virtual image. So I suppose I could do this, 1 over S, or 1 over 25 plus 1 over negative NP. I hope your book does it this way. I'm using NP to mean the absolute value of the image distance. NP is the 110 centimeters. Well, I know that the actual image distance is negative. Okay, so 1 over 25. This is where I would insert 1 over negative 110. Okay, let's plug those numbers in and find out what the power of this converging lens needs to be. 25 reciprocal. I'll do minus 110 reciprocal equals, power in diopters would need to be 0.03 diopters? Okay. Capital D for diopters. Or in other words, the focal length would have to be, oh, I just realized I made a mistake, didn't I? This is inverse centimeters. 0.03 inverse centimeters. How do I convert from inverse centimeters to inverse meters? A diopter is an inverse meter. So let me just leave that for now as inverse centimeters. I'll take the reciprocal once more, and that tells me that the focal length needs to be 32 centimeters. Is it positive or negative 32? We're talking about a converging lens. A converging lens has a positive focal length. So I could go back up here and instead of 25 centimeters, I could do 0.25 meters minus 1.10 meters reciprocal. Yeah, okay, so 3 diopters. The power, which is the reciprocal of the focal length, would be something like 3.1 diopters. That's the SI unit. Okay, evidently to convert from an inverse centimeter to an inverse meter, you would multiply by 100. Makes sense. That's the opposite of converting from centimeters to meters. Next up is nearsightedness. Let's go back to some images from your book. Okay, here's another defective eyeball. This is the defect that I have, I suppose. I know I'm nearsighted, and I guess for most nearsighted people, according to your book, their eyeballs are a little too long. So if you're nearsighted, for the usual reasons, you've got long eyeballs. You're long ball Larry. Here are rays coming from a very distant object, like a mountain or the moon. A normal eyeball has the retina right about here, where the dashed line is. That's where those parallel rays would converge. But you unfortunately have a slightly long eyeball, and so the rays have already converged before they get to your retina. They start to diverge again, and the image formed on your retina is blurry. That's what's happening if you're nearsighted and you're looking at a mountain that looks blurry. Those rays have already started to spread out again before they hit the light-sensitive cells on your retina. So A nearsighted person has something called a far point. Just try to remember that connection. A farsighted person has a near point, and a nearsighted person has a far point. What is the far point for a nearsighted person? It's the farthest point at which they can still focus an image of an object. So for me, it's not that far. If I put a book, look, I'm sitting in my chair right now. If I take my glasses off, whew, I've got a bunch of VHS tapes about 8 feet from here. I can't read a single one of them. I mean, I know what they say because I've had them for a while. I know that Cheech and Chong's Up in Smoke is sitting right there on the middle shelf, but I can't actually read that. In fact, even if I put it 4 feet from my face, I can't read it. So my far point is obviously closer than 4 feet. And in a moment, I'm going to calculate my far point by using an old lens prescription that I got from an eye doctor. Okay, so what is the far point for a normal eye? How far out can an object be for a normal eye and still be focused on the retina? Infinity. A normal eye can focus something that's super far away. Somebody who's nearsighted can only see things that are near. They cannot focus on things that are far. So how are we going to correct this defect? Well, since we're able to see, since a nearsighted person is able to focus on something at its far point, at their far point, but not any closer, then an object that's beyond the far point, like a mountain, in order to focus an image of the mountain, we need to produce an image of that mountain at the far point. The whole point is to take your object, use a lens to make an image that's at your far point, because you can actually focus something that's at your far point. Okay. And for that, we'll use a diverging lens. Remember, diverging lenses always make virtual image. So once again, the final image that we're talking about is still virtual, and that means that the image distance will still be a negative number. Oops. Let me go back here. Elongated eyeball, right? This is what I wanted. Okay. So I'm just going to pretend this is a penny. No, take that back. No, a mountain. Yes. Suppose you would like to look at a faraway mountain. So the actual object, the mountain, is at infinity. Our distance s is going to be infinity. But we want the image produced by the lens to be at the nearsighted person's far point. Let's do an example to make that clear. But you'll see, or you'll notice that incoming rays without a corrective lens, they converge too early. The effect of a diverging lens is to spread those rays out a bit so that when they reconverge, they actually don't reconverge until they get to the retina. Previously, they converged too early. Now they converge at just the right place to focus on the retina. Okay. So let's look at an example of correcting somebody's myopic vision. And for this purpose, let me grab my old lens prescription. Here is an old invoice from Zenny Optical. Love this company. I'm not doing commercials for them here, but if you're nearsighted or farsighted and you need new glasses, did you know you can get glasses for $8 online? They're not the only website that does this now. There's a few places, I believe, where you can order super cheap glasses. And a lot of them look fine, at least to me. I mean, maybe you think my glasses look terrible, but much more affordable than Lens Crafters, for instance. But here's some specs for my lenses. I don't understand all this detail. They've got something about cylindrical, spherical. I know there's a astigmatism. I'm not familiar with all the terminology, but I believe the quantity I'm interested in is the spherical correction. And this is the power of the lens. Notice that it's negative. And negative power, well, power is the reciprocal of focal length, which means the focal length is also negative. What kind of a lens has a negative focal length? That would be a diverging lens. So I must be nearsighted. I'm going to use this lens power to deduce what my far point is, and then I'll check to see if my far point is consistent with that number. So given let's suppose that this person's, what is it, prescribed lens power is, and you may have noticed, look, the number, oh, take that back. I thought the numbers were going to be different for my two eyeballs because they're often different between the eyes, but at least my eyeballs are consistent with each other. That's good. Prescribed lens power is negative 2.25. Okay, remember, this is the reciprocal of focal length. So I know that they use diopters. That's, in other words, inverse meters. What can we say here? 1 over S plus 1 over S prime is equal to 1 over F. This number, this is the reciprocal of focal length already. So we just plug that in here, negative 2.25. The object. Remember, the purpose of corrective lenses for somebody who is nearsighted is to allow them to see something that's far away. And the farthest thing I can imagine would be infinity. So we let the object distance equal infinity. What does the image distance need to be? Well, somebody who's nearsighted has something called a far point. That is the farthest point at which they actually can focus even without a corrective lens. So we want to take the object, this mountain, and produce an image of the mountain at the person's far point, because then their eye will be able to accommodate and make an image of that on the retina. S prime would be, I'm going to call it negative far point, because again, a virtual image has a negative image distance. I'm going to use FP to refer to the absolute value of that distance, just how far the far point is from the eyeball. Okay, so we can cross that out since S is infinity, and that leaves us with 1 over negative far point equals, and here's where I will insert negative 2.25 inverse meters. So the diopters, which are the same as inverse meters, this is to remind me that this quantity over here is in inverse meters. After I take the reciprocal, my far point will be in meters. Okay, minus signs cancel. And according to the equation here, my far point would be, I just take the reciprocal of 2.25. That's 0.44 meters. In other words, 44 centimeters. Okay, so before I test this myself, quick little sketch. Here's my eyeball. Pupil. Optical axis. Looks like my eyeball's shooting out a laser beam. That would be awesome. Maybe that's the superpower I would go for. People always like to ask each other, if you could pick any superpower, what would it be? I dated somebody who said her desired superpower would be speed reading. Wasn't sure how to feel about that. Okay, so if we've got an object at the far point, maybe I can only see out to 44 centimeters. Well, that's what the equation is telling me. So this object is just barely able to be focused on my retina. And I should have drawn this eyeball a little longer. That's the whole point. If I were to look at anything farther out than that, okay, I'll exaggerate the length of the eyeball a little bit here. Anything way out here, for instance, and even if my lens is as relaxed as possible, so I will draw the lens real thin, those ciliary muscles are not contracted at all. Sorry, this wasn't the lens, that was supposed to be the pupil, iris. I know your pupil's not that big. It shouldn't be. If your pupils are that big, you gotta stop doing drugs. So this, I first will draw the undeviated ray. The idea is, let's see, yeah, these rays are going to converge too early. Not a great drawing, I understand that. Oh, come on. So when something's this close, fine. The rays will converge at just the right spot. But by the time you put the object way out here, past the far point, this is the far point, past the far point, the rays converge too early, right here. Again, not a great drawing, but you want to spread those rays out a little bit. That's the whole point of inserting a diverging lens, is to spread those rays out a little bit so that they take longer in space to converge. Get some practice from your homework. There's some examples in the book, of course. You should know how to correct either nearsightedness or farsightedness using the thin lens equation. Don't forget, a nearsighted person has a far point. A farsighted person has a near point. For both cases, the image produced by your lens will be a virtual image, which means a negative image distance. Don't forget the negative sign. And lastly, somebody who is nearsighted would use a diverging lens to correct their vision. Somebody who is farsighted would use a converging lens. And I know you can't see this, but while you're listening here, I'm gonna hold a piece of paper out. Let me take my glasses off. I'm holding a piece of paper away from my face. I've got a ruler sticking out perpendicular from my forehead, and I'm gonna move this paper towards my face until I can actually read it. Okay. So just about now, I can now read it. This ruler is 30 centimeters long, and I would estimate that the paper is about 10 centimeters past the ruler. 30 plus 10, there you go. If I put anything closer to my face than about 40 centimeters, I can no longer focus on it. This number seems legit. Of course, it's been many years since I had my eyes checked, so probably time to update that prescription.